This video will demonstrate the benefits of IoT PML, such as transparent and efficient development of IoT software on a real example solution for detection and classification vehicle in real time. The objective is to detect different car types in real time in live camera feed. Potential use cases in a field are road toll, surveillance, transport logistics, and theft detection. Laptop PC uses webcam to get video input for the detection and the screen to show video stream with detection results to the viewer. PIN-Z1 board does the vehicle detection from the video input using tiny YOLO object detector to get vehicle locations and vehicle classes such as car, truck, bus, and motorcycle from the frame. The vehicle detection and determination are based on neural network algorithm. In our demonstration, IoT PML is used for top-down design flow, allowing us to refine system architecture and functional interface, enabling separation of interface definitions and system functionality visualized in different abstraction levels. For our demonstration, we used all 4 identified architectural views, such as system context, system decomposition, software stack, and threat model. So let me first show the system context of the vehicle detector. So the system context shows the external entities which are interacting with our system under design, in our case vehicle detector. We identified that the external entities are camera, providing the video stream towards the vehicle detector, and vehicle detector sends out the video stream including vehicle information to the monitor. Also, the vehicle detector provides vehicle detection data which are consumed by the service called software application. As a second step, what we did, we used the system decomposition diagram to visualize the system components of our system under design. So what we did, we identified at the highest level that our system is comprised of the pink board and the PC. In the first iteration, obviously we use the system component, and then we assign whether it's software or hardware component based on the type of realization. The pink board as a hardware component is comprised of a processing system and FPGA. And lastly, the processing systems also serves as executable environment for software component, which is called tinier YOLO. On the right hand side, we have the PC, which is represented by the laptop. And on a laptop, there is running a PC application. So as a second step, what we did within the system decomposition, we identified the interaction points of each components, what you see over here. And the result looks like this. So we have the vehicle detector, this time is visualized as a boundary. And here we have all those components, system components, which we identified in a previous step, such as the PC, pink board, and so on and so forth. What we also identified, we identified the external interfaces, which in this case are realized as interaction points. I'm talking about a USB, Ethernet, HDMI, which serve for the purpose of communication with our external entities identified in the first step in a system context view, such as camera, software application, and a monitor. As you see over here, we see clearly again what type of information items are being conveyed using which type of interaction point. Here we see internal communication between the PC component and a pink board using a pink SOC Ethernet as an internal communication channel. And here we have the AXI bus, which is used to communicate between the hardware component and FPGA hardware component within the PINC board. Also, at this level of abstraction, we performed behavioral analysis, which discovers a concrete sequence of a concrete scenario. In our case, what we did, we used a regular UML sequence diagram to depict the only scenario, which is called display a vehicle type on a monitor. So let me show you that. Here we reuse the already identified components from the diagram, what you just saw, the system interfaces a minute ago. Here you can clearly see the sequence of messages leading towards the goal, which is the display a vehicle type on a monitor. So it all starts with the camera sensor, which sends some video streams through the USB to the hardware component of PC. Within the PC, there is some pre-processing activity happening, and the PC hardware component sends the pre-processed video frame through the PINC SOC Ethernet communication to the PINC board to the pre-processed video frame, which then is forwarded towards the processing system hardware component. Then there is some processing which adds the CON0 layer on it, and then the processing system sends to FPGA hardware component the CON0 output using the AXI bus. In the FPGA component, there is a processing the layers from 1 up to 7, and then it sends back the CON7 output using again the AXI bus to the processing system, and then the processing system adds one more layer, CON08, to it and sends to the PINC board through the as a network output towards the PC component the result, network output. Then in the PC component there is network output post-processing, and in fact drawing the detection into the frame so you can visually see what was detected, and then this detection is added as another layer to the video stream, and you see that as a video stream including vehicle identification on the monitor. Okay, so that was the behavioral analysis. Coming back to the architectural views, and then what we did within the software stack, which is the pure IoT PML implementation. Since this vehicle detector is using shared components and is operating at a very high level, software level, we identified that we need only within the software stack to model the application layer. The rest, such as the platform layer, is just, I will show you later, it's just depicting how it could be solved if there would be another solution modeled requiring modeling concrete hardware components. Okay, first let me show our application layer within the software stack. So the first step, we identified application interfaces which are needed to for the internal communication. So we identify all these interfaces and added a concrete behavior which is needed. Then later we use the application implementation package, and what we did, we in fact decomposed those two software components into another software components, just like what we did in case of the system decomposition. We did the same thing but for the software components. So here we have the tinier YOLO CNN, and here we have the PC application. just to remind you what we are looking at. So here is the decomposition, what you saw previously. That's the decomposition of the software component and PC application. So here it is. The tinier YOLO is comprised of another software component, run CC, and CNN communication. And here we decompose the video stream software component into following software components. Another step what we did within the software stack, we created in the implementation, we assign a concrete interfaces which are either implemented or used by the identified software components. So it gave us a great opportunity to identify which interfaces, software interfaces, are external and which ones are internal. This diagram is looking very chaotic, but believe me, this is just for the sake of creating the relationships. It can be visualized to be concrete in enterprise architecture using relationship matrix or in some tabular manner. So, and that was it, what we did for the application implementation. And then later we created in the package application design the view of software components of our vehicle detector using our identified interfaces. You also, what you see, the connection between the external interfaces and the software parts of your system. So that's very nicely. I will make it smaller. Okay. We also used the opportunity, since we had that very nicely laid out on a diagram, we used the opportunity to assign concrete non-functional qualities to concrete components. In this case, what we just did, we assign this requirement on memory footprint on a software component run CC, which has to be lower than 5 megabytes. This gives us a concrete requirement for the production of the software. So then we depicted the behavior specification of the high level of abstraction component PC application, which looks like that. So the video processing starts with initiation, then it reads video input, goes to the pre-processed image, and then sends receive vehicle detection data. And we use the opportunity to define control points of this behavior specification, which in our case, there are requirements that the flow starting from here, read video input, up to here, up to the recognition, cannot be slower than 1 second. So that gives us great opportunity to define the NFQ duration type restrictions. Last but not least, as I already mentioned during the software stack, if our system requires to model hardware, then we would use the hardware layer within the software stack, which that would look like that, and we would use the either this to define the IP exact definition, or the other way around, we would use the IP exact if available, which after the import to the model, that would create a diagram within the hardware layer included in the software stack. Okay, so that will be it for the software stack very quickly. Last thing what we did, we created the threat model, which identified the potential threats for our solution. Security threats, for that we use specially developed threat model diagram type, which is a part of the IoT PML framework implemented in enterprise architect, which helped us to identify potential threats according to the trust boundaries. So with that, that will be it. This whole exercise using the modeling framework to capture all the description of the system really helped us to identify potential design flaws. And here is an example how even high level of abstraction depicted using the IoT PML framework can help us to trace to the code.